Welcome to The Explainer. Let's jump right in. Today we're tackling a massive headache that basically every developer runs into when they step into the AI space. The source material gives us a literal blueprint for taking a basic toy AI script and transforming it into a scalable, highly observable, production-ready application. We're moving way past those simple weekend hacks today to look at the actual architecture that makes an app survive in the real world. Because here's the harsh reality, right? You've probably built some super cool, fun AI projects on your laptop. And hey, they're fantastic for learning. But the second you deploy those projects into the wild and expose them to real users, they usually crash and burn. Why does that happen? Well, it's because they're flying blind. They're totally missing the critical infrastructure you actually need to handle the sheer chaos of real-world internet traffic and completely unpredictable API connections. So, here is our blueprint for today. 1. The AI production problem. 2. What is RAG? 3. The architecture stack. 4. Vectors and data prep. 5. Orchestrating with ingest. And 6. The final application. All right, section 1. The AI production problem.
This right here is the great divide. On one side, you've got your fun weekend project. If the OpenAI API hiccups for even half a second, the whole thing shatters and your user is staring at a terrifying error screen. Not great. But on the other side, you have a true production-grade app. Going to production means you absolutely must have deep observability. You need to see exactly what your app is doing at every single microsecond. You need automated retries, so if a connection drops, the system just quietly tries again. And of course, you need rate limiting to prevent a single user from completely draining your API budget.
Moving to section 2. What is RAG? So RAG stands for Retrieval-Augmented Generation. The absolutely crucial takeaway here is this. Instead of just crossing our fingers and relying purely on an AI model's base training, which, let's be honest, can lead to it totally hallucinating answers, we are actually physically augmenting the AI's prompt with our own specific private data. It's kind of like giving the AI an open book test. We hand it the exact paragraph from a private PDF that holds the answer, and we say, hey, reason strictly based on this specific information and give us an answer. The workflow goes a little something like this. Step 1, you upload your raw document, like a contract or an invoice. Step 2, the application runs a lightning-fast vector search to hunt down the most relevant information inside that document. Step 3, we grab that relevant info and pass it straight into the prompt for the large language model. And finally, step 4, the model outputs a highly precise, context-aware answer. Section 3, the architecture stack.
If you want to build this robustly, here is your go-to toolbox. We're going to use Streamlit for a really clean Python-based front end, and Quadrant as a high-performance local vector database. Now, to read and parse those raw PDFs, the blueprint utilizes Llama Index. The actual AI brain reasoning through all this data, that'll be OpenAI's GPT models. And finally, tying the whole shebang together securely is Ingest, which is an open-source tool handling all of our orchestration and observability.
Section 4, Vectors and Data Prep. You hear the term vector database thrown around constantly in AI, but what is it really? A vector database, like Quadrant, takes human-readable text and basically converts it into a massive mathematical array of numbers. A vector. This lets the system compare the mathematical similarity between whatever a user asks and all the text sitting in your database. It's what allows us to instantly pluck out the exact right paragraph from a 1,000-page document in literally milliseconds. Think of this whole process like a data factory. We can't just shove a 1,000-page PDF into an AI all at once. First, we load the PDF. Then we have to chunk the text. In our blueprint, we split the document into chunks of 1,000 characters. But crucially, we use an overlap of 200 characters between those chunks. Why do we do that? Simply so we don't accidentally slice a vital sentence right in half and lose all the context. Next, we embed that chunk, which just means OpenAI translates it into that math array. And finally, we upsert, or insert it, into our Quadrant warehouse. Now notice this highly specific number, 372. When we use OpenAI to embed our text, it generates a vector with exactly 372 dimensions. That is the size of the mathematical array. It's an absolute deal breaker that when we set up our local Quadrant database, we configure it to expect exactly 372 dimensions. If the database shape doesn't perfectly match the OpenAI output shape, the entire factory completely breaks down.
Section 5. Orchestrating with ingest.
So, ingest is absolutely our secret weapon here. It acts as this incredibly resilient middleman between our user interface and our back-end API. When we wrap our AI functions in ingest, we unlock some serious superpowers. We get deep observability, meaning we get a visual dashboard showing us exactly how long a specific API call took, down to the millisecond. We also get automatic retries, API throttling, and the power to handle tons of concurrent users seamlessly.
As the creator of this source material pointed out, flying blind is just a guaranteed recipe for failure. To quote them directly, when we actually want to go to production, we need to see what's happening. We need to have retries, throttling, and observability. Without this layer, a simple timeout from OpenAI just results in a dead app and a really angry user. But with ingest, the app intelligently manages that traffic and catches those errors.
And this brilliantly illustrates how ingest actually achieves that resilience. Instead of writing one massive, super fragile block of Python code, we break operations down into isolated steps. Step 1 is loading the PDF. Step 2 is embedding the text. Step 3 is querying OpenAI. Here's the magic. If step 3 fails because the internet drops, ingest simply pauses and retry step 3. It doesn't force the user to re-upload their whole document and start from scratch. That is a total game changer.
All right, our final section. Section 6, the final application. Here's what the finished production-grade blueprint looks like when all those gears perfectly synchronize. A user uploads a private document through our clean Streamlit UI. Llama Index dynamically chunks that text with perfect overlap. That text is embedded and becomes instantly searchable via the local quadrant vector database. The retrieved context is passed straight to OpenAI for intelligent reasoning, and the absolute best part? The whole flow is orchestrated safely by ingest, ensuring rate limits are respected and transient errors are automatically retried without the user ever noticing a hiccup. We've just taken a fragile script and totally transformed it into a robust, observable architecture that won't snap the second it hits the real world. You've seen exactly how vector databases, smart chunking, and deep orchestration all fit together to make AI genuinely useful. You have the complete production blueprint right here in front of you. The only question left is, what are you going to build next? Thanks for joining me on this explainer, and I'll catch you next time.